Okay, so today we're going to look at the canonical distribution. This will be our first foray into some real statistical mechanics. So imagine a system where you have a large heat bath or reservoir, whatever you want to call it. We'll call the reservoir sigma naught. And here's a system in contact with the reservoir. We have a constant volume. This reservoir is at some temperature T. Here's a small system, we'll call it sigma, and it is at some different temperature. So lower temperature, we're going to transfer some energy from the reservoir into the smaller system, a very small amount of energy, and raise an energy level. Okay, so thinking of this transfer, this is sigma naught, this is sigma, this is at T, everything's at a constant volume. Here comes in a little bit of energy delta E. All right, delta E raises some energy level E2 to E1, or changes some energy level from E2 to E1. All right. Let the internal energy of sigma naught equal U naught. Okay. Probably should have written that the different way, but the idea is that sigma naught is at some internal energy U naught. So the new internal energy for the reservoir is going to be U naught minus delta E, because the reservoir lost a tiny amount of energy delta E just by conservation from transferring it into sigma. So let's look at approximate the change in entropy. Okay. So we'll approximate the change in entropy, and that change in entropy can be approximated like this. Delta S is equal to the change in S with respect to U at constant V times, this is U minus U naught. This comes from expanding the entropy about U naught, small change, and looking at the first term. This is ignoring higher order terms. But U minus U naught is equal to minus delta E. And we know from what we've done previously that this change in entropy with respect to the internal energy at constant volume is what we call T. I'm sorry, 1 over T. du ds at constant V is T. So ds du at constant V is 1 over T. So that means from what we have up here for the approximation that delta S is equal to minus delta E divided by T. So this change in entropy is simply just this little change, the negative of this little change in energy divided by T. We know, so recall, that there's a relationship between the entropy and the number of accessible states. Omega is equal to e to the s over Boltzmann's constant Kb. So we're going to look at the probability ratios for these energy levels, or these states. And let's, I'll say look at the probability ratios, or ratio, for sigma to be in states 1 and 2. Okay. So if we look at the probability of state 1 divided by the probability of state 2, this number of accessible states is directly proportional to the probability, so we can write omega 1, this ratio is the same, and that ends up being, from what we have here, this is equal to e to the delta s divided by kb. Just because this omega is e to the s over kb, all right? Okay, so putting this delta s that we had over here into here, we get P1 divided by P2 is equal to e to the minus delta e over kbt, which equals e, that's little e, to the E2 minus E1 divided by kbt. All that's in the exponent. I hope that's clear. So let's take this and rewrite it as, this is equal to e to the minus E1 over kbt divided by e to the minus E2 over kbt. So now, looking at these probabilities, this is the probability ratio of a transition, okay, from 1 to 2, or the way I wrote it, the author writes it 2 to 1. Okay, so thinking about all the states in pairs, so if we take all the possible states in pairs, every possible combination in pairs, for a single energy state, EI, meaning like you're looking at holding this and looking at all the pairs that you could get from that energy state, okay? You're going to get something that for a single energy state E sub I, all right, the probability of that energy state E sub I is equal to Z to the minus 1, and we'll get to that in a second, E to the minus E sub I over KBT. You're going to get something of this form where this is the normalizing constant, okay? So Z to the minus 1 is the normalizing factor. Boltzmann's factor, this is what's called Boltzmann's factor. KB is Boltzmann's constant. The Boltzmann factor is just this, E to the minus E sub I over KBT. Okay. So we now are going to define something called the partition function. And this is going to become important for us because once if we can write down the partition function for a system, we can find out all the thermodynamic properties of the system that we're interested in. And we'll see how to do that eventually. So for the partition function, okay, we know that if we sum over all the possible states, the probability, if we sum, so I'm just summing this. This is Z to the minus 1 times the sum over I of E to the minus E sub I over KBT. And that must equal 1. That equals 1. We're summing over all the probabilities. That must total up to 1. That's what we demand. So Z is equal to the sum over I of E minus E sub I over KBT. So Z just becomes this summation. All right. So we let beta make some substitutions like we always do. We called 1 over KBT beta. So let beta equal 1 over KBT. Then Z is equal to the sum over I of E to the minus beta E sub I. Okay. All right. But we may have degenerate states. Meaning states that have the same energy And if you have a large system, you're guaranteed to have degenerate states where you have multiple states with the same energy. So let EJ be the energy of the state, or be the energy level. Here we were summing over the number of the states with energy. Now we're letting EJ be the energy level. We're summing over I, we're summing over all the states, okay? Now we're summing over the energy levels. So let EJ be the energy level and GJ, or G sub J, be the degeneracy, okay? Okay, so let EJ be the energy level and GJ be the degeneracy of that level. So say you have an energy level 3 and there are 27 states with that energy level, then, all right, that's the degeneracy of that energy, okay? So now we can write Z now we can write Z as, it's really the same idea, it's just summing over the energy levels now instead of the states. Okay. Summing over J, GJ times E to the minus E sub J over KBT. Okay. And that's equal to the sum over J of GJ E to the minus beta EJ. Okay. That's summing over the energy levels. All right, we can calculate based on Z, which we have here. This is summing over the number of states. Can calculate the average energy. That's just equal to the sum over I of P sub I, E sub I. Well, that's equal to Z to the minus 1 times the sum of E sub I, little e to the minus E sub I, or just, I keep wanting to write 1 over KBT, but it's just beta E sub I, okay? That just comes from the probability of a state multiplied by the energy of that state. Summing over all of them, you get the average energy. All right. So we can recognize some things in this expression and make this average energy come out to be just a function of Z and beta. All right. So let's look at look at dz d beta. Well, dz d beta is equal to the sum over I times minus e sub I, e to the minus beta e sub I. That's just taking the derivative of z with respect to beta. Okay? Now, but this is this, right? With a negative sign thrown in. So we get that the average energy is equal to minus z to the minus 1 dz d beta. Okay? But the derivative of the ln of z with respect to beta is equal to z to the minus 1 dz d beta. So the average energy can be written as minus d ln of z d beta. That's going to become very important for us because if we can write down an expression, if we can find the partition function z, we can use this to calculate it, and we'll see eventually how we can calculate all of these thermodynamic potentials, thermodynamic quantities that we're interested in using this partition function.